Hey engineers, and welcome back to 2.1.6 part 2. We're calculating the forces in a truss. And if you remember back to where we were going, we had a truss right here. And what we're trying to do is we're trying to find the forces in each one of these members. Because I said we could make this out of popsicle sticks. We could literally cut these to length to the right angles. And then the question is, which one has the most force on it? And then could you beef that up a little bit, or are there ones that don't have much force on it, and you could make that one a little bit thinner? Some of these are going to be in compression, so we're squeezing them. Maybe wood is better in compression than tension. So maybe you want to use different materials depending upon, is it being squeezed or is it being pulled? So that's where we're at. That's where we're going, is we're trying to figure out how much force is in each one of these members. And we had talked about there's two different types of forces. You can squeeze them, which is called compression. You can pull them apart, and that's called tension. A truss has triangles. Triangles prevent what's called racking. We've got our different supports. You've got a roller, which has one, and a pin that has two. And we had talked about members and reaction forces and joints to figure out whether or not a truss can be solved. So sometimes trusses cannot be solved because they don't have the right number of reaction forces to joints to members, and sometimes they can be solved. And then we're going to use these three ideas, that the torques equal 0, the forces left equal right, and the forces up equal down. And I had started you down Mr. Hare's steps to solving a truss. And so we made a master drawing. So we went over and we made a master drawing. We found all the angles using sine and cosine. So we took the opposite over the hypotenuse. So we found this angle, 53 degrees. We found this angle, 30 degrees. And with complementaries, that's got to be 60. That's got to be 37. And then we broke every joint down into a sub-drawing. So I kind of made a really haphazard sub-drawing here. And here's a better drawing. So this actually looks, and I would totally recommend this, and I wish that I would have done it in the first place. I took each of the joints A, B, C, D, and I put letter C, and I put every force. So this is from B to C, and so you said B to C. And then here's the force from C to D. And then, so these are interaction pairs. So if I can figure out this force and this force are going to be the same. So I copied over all of my angles, and I made what's called number 4, break every joint into a sub-drawing. I made a free body diagram with angles for every joint. Assume that every joint, quote-unquote, pulls. So that's why I made every arrow going from my drawing. So I want you to pause here, and I want you to copy down this drawing of all of my sub-drawings from my master of each joint. Joint A, joint B, joint C, joint D. Take a minute and get this down in your notes. All right, you're back. What we're going to do next, step 6, focus on the simplest joint. Use components of forces to solve for any unknown force using equilibrium. Here's what I mean by that. I'm going to go and I'm going to focus on joint A. Joint D is complicated because it has 4 forces, and I don't know any of them. I know the 500. Ooh, here, let me just show you a few things. So right off the bat, I know that this has to be equal to 500 because everything pulling down has to equal everything pulling up. So that's got to be 500. Ooh, and if this is 500, that also means that this is 500 because that's their interaction pairs. So this is what we're doing. We're going through trying to figure out some stuff. And we picked the low-hanging fruit right away. Force BD equals 500. And it is, since it's pulling, this is in tension. Letter T. So I'm going to go back and I'm going to update my master. So I'm going to go back here to my master right here. I'm going to delete some of this stuff. Oh, it's already, there it goes. I know that this is 500 pounds and it's in tension. I'm going to put the letter T there for tension. So that's how much force is on this member right here, 500 pounds. Let's focus on joint A. I'm going to go to the next page, and I'm going to redraw joint A. Joint A has got a force here. The force from A to B. It's got a supporting reaction force, which we found back in step number 2, I believe, which was 350. And there was a force pulling this way. And this is force A to D. So this is I'm just zooming in on joint A to see if I can figure out AB and AD. Now, check this out. This force right here, force AB, it has to be pushing down. Do you see that? Because this right here is pushing up at 350, this one has to be pushing down at 350. This component has to be 350 because all of the forces up and down have to add up to 0. All the forces left and right have to equal to 0, and all the moments have to equal to 0. I'm leveraging this right now, and I know that that piece right here, that component, has to be 350. And not only that, we found this angle right here from before. We know this is 53 degrees, so this is 27. I can use sine and cosine to figure out AB right now. Let's do it. I'm going to use the cosine. I'm going to say the cosine of 27 degrees is the adjacent 350 divided by the hypotenuse, which is the force from A to B. So I take 350 and I divide by the cosine of 27, and I've already done that to save a little bit of time. So that force at AB is 438. Now, it's not pushing up and to the right. That's not the sense. This force is pushing down and to the left. So this is not in tension. It's not pulling. It's pushing. This is in compression. And the force is 438 pounds. Now, I can figure out this piece. I can figure out this component, FAB, in the x direction. I can use the Pythagorean theorem. I can say I can go a squared plus b squared equals c squared. So I can say 350 squared plus force of AB in the x direction is equal to 438 squared. So this force of AB in the x direction turns out to be 264. So now I know that this is 264 pounds. And what's important about that, why I found that, is because that is what this right here. Everything pulling to the left equals everything pulling to the right. This equals 264. Do you see that? Do you see how everything pulling to the right equals everything pulling to the left? Now everything pushing up equals everything pushing down. And I use the Pythagorean theorem, a squared plus b squared equals c squared. And that's what this is. So I just used a little bit of my equilibrium. Up equals down, left equals right, sine, cosine, tangent, a little bit of math ninja. And I figured out two of my things. The force A to D equals 264. I'm going to update my drawing now. Go back to my master. I'm going to update this one first. I figured out that this one right here is 264. And this one right here is equal to, it's going the opposite direction, so I'm going to erase it. And I'm going to draw it going this way, which means I have to erase this one up here, and I draw this one going the opposite way, and that's 438. If this one's 264, that means that this one's 264. And if this is 264, that means that that one's 264, right? Because everything pulling to the left has to equal everything pulling to the right. And if this is 264, that means that this is also 264. See how this is coming down like a house of cards? And now so we're doing well. We're doing well. So I just figured out, I'm going to go back to my master here. It's really busy. I know that this is 264 pounds. And it's in tension. This is also in tension. This one is under 438 pounds. And remember how we reversed the arrows? That's in compression. That one's being squeezed because we reversed those angles or those arrows. This one also here. We know this one here. This one's 264. And this one's in tension as well. So, all we got to do, we just need one more member and we got this thing licked. Let's see if we can figure that out. We're going to go back to here and we're going to focus on joint C. So what I'm going to do, I'm going to recopy down C knowing what I know now. So I'm going to go to a blank sheet of paper, spot that's open. I'm going to put down joint C. And I know that there's a force on it going up at 150. I just figured out that it's being pulled this way at 264. And there's some unknown force that I don't know. So, here's what we got. Since this thing since we're being pushed up at 150, because everything, all the forces up have to equal all the forces down, this force needs to push down, which means that I need to change the sense of this around. This has to push down. It's in compression. I switched it around, and I know that this piece has to be equal to 150. Not only that, this has to push to the right. It has to push to the right, 264. That's the only way that this thing is in balance. It's in equilibrium. Everything pushing to the right, 264, equals everything pushing to the left, 264. Everything up equals everything down now. Now I can figure out this force at CB. I can use the Pythagorean theorem. I can go a squared plus b squared equals c squared. So that force at CB ends up being 303. Again, I just solved it earlier and to save us a little bit of time. So I'm going to update my drawing. Go back here. I know that this is now 303. And I reversed it around, right? Remember I made it into compression? So I'm going to reverse around my arrows. And I'm going to do the same thing over here. I'm going to make the arrow going this way. That force BC equals 303. Go back to my master. All right, here. Update my drawing. I know that this is 303 pounds. And it's in compression. It's being squeezed. So, here we go. We can finally take a step back and look at this truss and say to ourselves, two of these members are in compression. They are being squeezed. This one's being squeezed, and this one's being squeezed. Which one's being squeezed more? That one. 75% more. No, 25% more. So if you're going to beef one of these up, you want to beef up this one right here. 25% more. That's all it really needs so that they could kind of handle that equally. Now you look at the rest of them. They're being pulled. This one's in tension, this one's in tension, and this one's in tension. Which one's probably going to break first? Right there. It's in 5. It's twice as much force on that member than the other two. So this is where engineering comes in, kids. Engineering is the ability to think before you do. We took a while, and we finally got here, and we were able to figure out which of these members is under the most force. BD is. And it's underneath tension. It's being pulled. So you want to make sure you pick a material that's good in tension. Like, for instance, fishing line. Fishing line is great in tension. Steel cables, great in tension. Concrete is horrible. Like, you can pull concrete apart. It's awful. But concrete is really good in compression. So, like, choosing your materials for where they are, this is engineering. Being able to use this math to make a prediction and figure out which of these materials is best suited for what the math says. Being smarter about your build. Thanks for watching. I know this was a long time, and you did good. I'm proud of you. Keep it up, kids.